my name is Guang, 12 years old. For this lesson, we'll be continuing with physical chemistry. For this lesson, we will be continuing from the Maxwell-Boltzmann velocity distribution. For last lesson, we have proven for the ideal gas law, right? So if you want to know about it, you can go back to previous lessons. But for this lesson, we'll be showing the formula of atmospheric pressure. So the formula of the atmospheric pressure is P equals to P naught. So P naught in this case, for this question, we are going to use the standard pressure at the sea level, okay? So for this part, then it will times e to the power of negative mgh over kt, which I'll explain later. So for this part, why is there a cube here? So for this part, just assume the cube of air. So assume that there's a cube of air, right? So this cube of air, we are going to count its surroundings. So this whole volume of the air, what we'll have is that we'll have it to divide by the below area, and we'll be left with the height, okay? So for this part, what we'll have is that, so first of all, what we're going to use is the definition of pressure. So pressure is basically P equals to F over A, right? The force over the surface area of contact, okay? So for this part, what we're going to have, so we need a small amount of pressure over here. We're going to use modulus for now because that we're not going to straight away go into just using the finding out whether it is increasing as it goes up or not. So later then we'll use it. So for this part, modulus Vp. So force over the surface area. So the surface area will still be A, while the force in this case will be the weight. It's about the gravitational force. Well, so over here for this part, it will be G times dm. So this mass has over here, it has a very small amount of mass, okay? So this part, so the weight is basically the gravitational force times the mass. And then what does mass equal to? So mass is basically density times volume, which density is rho. And here we'll have a very small volume. And then here we have G and then A. Okay. So what we'll have is that, so what is volume? So as I have said over here, there's the area and then there's the height. So here the volume is the area times the height, which is in this case a very short height, whereas for this we'll have dh and then g and then a once again. So now that we've gotten this, we can do with dp. So dp here. So if you're going higher and higher, so when you're at like if you go higher, the pressure, will it increase or decrease? Well, so the volume of the air will decrease, whereas we can call it that the air will become thinner and all. Like when you compare being very at the top of a mountain or at the steep of a valley here. So you can compare those two and you can tell that the air is definitely thinner as it gets higher, and when the volume gets smaller, the pressure will also decrease. So since it decreases as it gets higher, so it will be negative, and the A can be simplified to just become negative rho G D H. Okay? Alright, so what we'll have here is negative rho G D H. And now moving on to the next part, which we will have P. So P, we can just use the ideal gas law, which is P equals to small n. So the small n is the number of moles. The rho is the mass density of this volume. So for this part, it is N or T over V. Okay. So this is just the ideal gas law. You want to know more about it, go back to the previous lesson. Now that we have gotten both dP and P, we can find dP over P. So dP over P is basically negative rho g dH over nRT over V. And the denominator, this part can reciprocal and go to the numerator, and we'll get negative rho GV dH over nRT. So what is the densities times volume? It is the mass, right? But wait, why is this M capital? So apparently for this part over here, while the rest are still the same. So for the mass, it's the mass inside the volume of this cuboid. So for this part over here, we're talking about this cuboid, as it gets higher and all, as the height increases, as the number of particles will increase, the volume will increase, the mass will increase, and the pressure on the below surface will also increase. Okay? And despite all that, it will still be a negative. Okay, so for this part, what we have over here will be, so this will be equals to, so N is the number of moles, right? Basically, it is equals to so numerator stay the same, the mass inside the volume over the molar mass. For that will be the number of moles there are. And here you have RT. So apparently the two capital M's can simplify, and this will be able to reciprocal to the numerator, which will become MR times G dH over RT. So what is MR equals to? So molar mass, it is equals to the mass, so the small m is the mass of one molecule, and then it will times GDH, and then it will also times the Na. So wondering what Na is, it is the Avogadro's number. Okay, so Na is the Avogadro's number. While over here for this part, the Na can go to the denominator of the denominator, whereas we'll get R over Na times T. So what is R over Na? R over Na is, so the rest will still be the same, mgdH. So for this part, R over Na is the Boltzmann constant, Kb. And then here you have T. And now that we have gotten this, we can integrate on both sides, whereas one side is dP over P, with the range of the P naught to P, and then the other side can take out everything that's unrelated to H, which is mg over kBT, and it will be ranged from 0 to H, and then here we'll have dH. Okay, so when we integrate both sides, so 1 over P, when you integrate it, becomes ln P, right? And after we sub it in, it will become ln P minus ln P naught. But ln is like ln something minus ln some other thing. It will become divide inside the ln, okay? So it's like ln x minus ln y is ln x over y, which in this case will be P over P naught. And it will be equals to, so apparently you integrate, you get H, you sub in the boundaries, you'll still get H. So it become mgh over kBT. Okay, alright, so now that we have gotten this, we can use it the exponential for both sides, which will have e to the power of. Well, for this side, it will be cancelled off with ln for their inverse functions. So you get p. So we can move the p naught to the other side, which will be equals to p naught. P equals to p naught e to the p power of mgh over kbt. And thus it is proven. The only difference is that I added a b, that's all, but both of them are both Boltzmann constant. Well, if I want to get another result, you have, so both numerator and denominator you can over the Avogadro's number because they can simplify otherwise. So both numerator and denominator, for the numerator is m over the Avogadro's number, the mass of each molecule, and the denominator will be the Boltzmann constant over the Avogadro's number times t. So over here, what we'll get for this part is that, wait, let me give, oh wait, whoops, so for both sides times of the Avogadro's number. So over here what we'll have is over here what we'll get from this part will be so what we'll get over here will be so the mass of each one molecule or particle times the Avogadro's number is the molar mass, which will be mRGH, and then we'll be overing, so the Boltzmann constant times the Avogadro's number will be R, the universal ideal gas constant. Okay, so this is another result that we can get. Well, just for extra information, if you want to know what the P naught in this case is, it is basically 101.325 Pascal, basically, as it's in pressure. So over here, for this part, what we'll have is that, so we'll have this graph over here. So as you can see, for this part, the graph, we have the pressure and we have the height. So over here, the relationship between the height and the pressure will be like this. Okay, well, this part, it will definitely touch one point, and the point will be P0, so P naught, and then here it will keep going on. Okay, so that will be all for this lesson. So if you want to know more, it will probably be in future lessons. So let me just give you a quick look. And last but not least, thank you for your watching.